Hello and welcome to the first video in my series on quality engineering. Um, Over the summer, I actually had an internship in the quality department of a manufacturing company, and one of my tasks was to dive into normality a bit because there's kind of this new normal revolution where a lot of companies are really pushing normality. And normality might seem to a lot of people coming, especially engineers who really don't care about statistics. They care about solving problems, and statistics isn't really solving problems, it's analyzing problems, not solving, right? So I used to have a lot of trouble with statistics. I didn't really like it. I didn't see the point until I actually got to use real data, and then I saw the actual defects, and it made a lot more sense. So I'd like to help with that a little bit because quality engineering really is a new field of engineering that's going to see a dramatic increase here very, very soon, especially with a lot of schools adding on quality engineering minors to different engineering fields. And with the Six Sigma thing that has been going on for a while is continually picking up more and more speed. It's kind of becoming an industry standard. You almost need to have it to get into the higher up positions. So here's kind of an entry level to it. I like explaining things to people because, especially when I'm new, and I like learning from people that aren't necessarily experts a lot of the time because they know where the hangups are, and that's me. I mean, I took a statistics course last spring. It made very little sense until now when I've actually done it. Now it makes a lot more sense, but now I know where I got hung up. So maybe the places I got hung up are where you got hung up. So that's kind of the point of this series, is to work through it with you, show you the math, so that you can so it can help you understand. So the place to start when it comes to quality engineering is we're going to be looking at a lot of data. And analyzing data, and one of the first things you need to know about your data is whether or not it follows a normal distribution. So what is normality? What is a normal distribution? Well, this is a normal distribution. You may have heard it called the bell curve. Um, it's that um, it's a specific type of probability density function. So a probability density function, um, as you can see on there, it's a function where f of x, the y, is the probability of attaining that value of x. Okay, and so in a normal distribution, there are two parameters. There is the mean, or the location parameter mu, and the standard deviation, or the scale parameter sigma. And so you probably know what the mean is. That's the average. Most likely you know what the standard deviation is. That's really a measure of how wide the data is spread. So using those two parameters, we can then plug in the x value that we want to and find out the probability of that x value occurring within the given set. Okay, so the normal distribution, according to this definition, is a continuous distribution function that is often used to represent random variables whose distributions are unknown. So that doesn't really make sense. Continuous distribution function means that there is um, a variable that has a continuous distribution. So what does a continuous distribution mean? That means that the values of that variable are not in nice, neat steps or buckets. They can be 0.001, 0.003, whereas something that wouldn't would be like, I'm trying to think, you have, oh man, I can't really come up with a great example of what I don't even remember what the opposite is, but a continuous distribution function. Maybe this will honestly help. Is since we don't have any other option, we know it has to be a continuous distribution function. That's why I think you know matching words is great at the beginning of the year when you don't know all the vocabulary, and then stuff gets muddled. But a continuous distribution function just means that you can have many variables. It's not in discrete steps. So a continuous variable or a discrete variable. So a discrete variable would be like 1, 2, 3, 4, 5, and then, or 1, 2, 3, 4, 5, 6. So like the numbers on a die. And then a continuous variable would be like um, the amount of rain, that we have, which could be anywhere from like 0 to 6 inches, but there's many infinitely small steps in between. And that would be a continuous variable. So this also says to represent random variables whose distributions are unknown. What that means is that that's kind of interesting because, well, we're assuming that it's a normal distribution, right? We know it's distribution. Well, no, we're assuming it. And we're assuming that for two really good reasons. So there's two main reasons it's important that normality is important in manufacturing. And the first is the central limit theorem, the CLT. You might hear this in your statistics classes. And what it says is, if sufficiently large samples, usually n is greater than 30, are taken from a population with replacement, so that means you take your samples out, more than 30 samples, and then you put them back in, the distribution of the sample means will be approximately normally distributed. So that means if you have, let's say, a population of 100, and you keep taking out samples of 30, if you do that 100 times with 30 random samples pulled out of there, then you take the mean of each of those 30 random samples. So you pull out 30 random samples, you take the mean, record it, put it back, take out another 30 random samples, and you do that over and over and over and over. If you were to plot the means of all of those samples, it would approximate a normal distribution. And then if you kept on doing that, so you did it one time, so now you have a distribution of the means, and then you did that again out of those distributions of the means, eventually it would form a perfect normal distribution. So this is important, and the reason that we want this is because if we know that the population is normal, then we don't have to have more than 30 samples. So that means if our distribution is normal, we don't have to take 30 because according to the central limit theorem, what that means is if we were to take an infinite amount of samples, it would eventually turn into a normal distribution. And in manufacturing, the more samples you have to measure, the more expensive it gets. So if we can say that according to our analysis, the data follow a normal distribution, we then don't have to take as many samples because we can just say, well, if we were to take an infinite amount of samples or even 1,000 samples, it would be normal, so there's no point in us doing it. So that's the main reason that we like the normal distribution, is because we can take less samples, saving us money. The second reason is in manufacturing, we use capability indices. So capability indices, you might hear them referred to as CP, CPK, PP, and PPK. These are statistical measures of the ability of a process to produce outputs within specification limits. So if you've ever worked in a manufacturing setting, or if you haven't, this might be one of the more important things to take away from this, is that when you manufacture something, you're given dimensions. But since it isn't perfect, they give you a tolerance on those dimensions. Because let's say you have a dowel and it needs to fit within the circle of the part that it mates into, right? That dowel has to be small enough that it can go in, but it has to be big enough so that the fit is tight. So there's a tolerance there. So they'll give you the nominal, which is considered that's what we want, that's perfect. But it can be plus or minus however many inches, millimeters, whatever your measuring is. It goes with angles too. It goes with all of the different dimensions you can. But what the capability indices say is they say, okay, our product is producing within the spec limits, so it's not making the part too big, it's not making it too small. And based on how high, and based on the number that we get for our capability index, it tells us how often we will be producing a good product. So these capability indices rely on an assumption of normality. If the data isn't normal, then the capability cannot be considered a valid measure of the process's ability to produce outputs within specification limits. So I'll explain a little more when I get the equation up. So the central limit theorem, we already kind of went over this. It's important because we can use it to assume that data is not perfectly normal, but it's normal enough. So we can do all of our analysis on it, because as long as it's kind of normal, we know it will be some if we were to take enough samples, right? So there is a limit to this, though. If the data do not fit a normal distribution close enough, and that's determined by our normality tests, we'll talk about that later, or other statistical methods will need to be used to make an accurate assessment of the processes. There's other distributions. There's Chebyshev's theorem, high capability exemptions, but basically, the central limit theorem says that if it's normal enough, we'll consider it normal and we're good. Okay, so that's why we like normal distributions. Other distributions don't necessarily have that. So capability indices, like I said. So what is a capability index? Well, there's two kinds. There's CP and PP. In industry, they'll usually use PP because that is using the sample standard deviation. We're not working with populations in manufacturing. We're taking samples, so we have to use the PP. Because it limits your degrees of freedom. PP is usually going to be lower than CP anyway, but generally we actually in industry like to use the PPK rather than the PP. And the PPK is nice is because what PP says is, okay, it takes your upper spec limit minus your lower spec limit divided by 6 times your standard deviation, your sample standard deviation. Now that's great, but that doesn't really tell us where we're located. So if your mean is not on nominal, it doesn't take into account of that. It just says, all right, you know, we're hitting in there. But PPK will actually tell you how close you are to failing at at the closest side. Okay. So that's why we like PPK. It just takes the upper spec limit and the lower spec limit, divides them up, and it will take the minimum because we want the smallest. We want to know what's the shortest distance. Okay. So to be able to use these, we need to test for normality, and there are multiple ways, and I'm not going through them all. I'm just going to take 3 main ones. These are kind of the standards that have been used in industry whenever I've used them. Well, the first 2 are the standards. The last one, I'll go into that a little bit later, but that kind of fits in. That's like a real last resort. Okay. So these work often. The Anderson-Darling and the Ryan-Joyner both, and yeah, the skewness-kurtosis does too, using the Jarque-Bera. They convert it into a p-value. So p-value is the probability of obtaining the test results if the null hypothesis is true. Now, statistics is all about definitions, so we have to define what that means, and that doesn't really make sense. I mean, it took me forever, and there are countless videos on p-values. I should honestly do a p-value in this series. I probably will. For now, that's not my focus. This is a very high-level introduction, just going over the basics, going over the general stuff. So what that basically says is a higher p-value, and it goes from 0 to 1. It tells you the probability of your null hypothesis being true. That's just the definition we're going to use for now. That's not technically correct, but it's going to get you where you need to be for this video. So it's based on whether or not your p-value is passing or failing is based on your significance level. This is often called alpha. The probability, so your significance level is the probability that a statistical test will reject the null hypothesis and accept the alternative hypothesis. The significance level for the Anderson-Darling test is 0.05. 0.05 is pretty much your basic significance level. So whatever your significance level is, if your p-value is greater than your significance level, it's considered a passing value and you fail to reject the null hypothesis. Okay? So fail to reject the null hypothesis means we accept it. But don't say accept the null hypothesis. That's not technically correct. You can say it for now, but get in the habit of saying fail to reject rather than accept. Although you don't say fail to reject the alternative hypothesis, you say we accept the alternative hypothesis. It's a lot of semantics, but that's what statistics is, because statistics is the science of arguing over numbers when they can look completely different to 2 different people. So that's why we care about semantics a lot. So if the p-value is greater than or equal to the significance level, then we fail to reject the null hypothesis. That means that the null hypothesis is true, the alternative hypothesis is false. Okay? So the Anderson-Darling normality test is one of the common ways that we test if data follow a normal distribution, and it's usually the first that's used. The Anderson-Darling test measures the area between the fitted distribution line and the actual data. The statistic, a squared, is a squared distance, so smaller values indicate a better fit to the selected distribution. A squared is used to calculate a prime squared, which can be used to calculate the probability that the observed data was obtained from a normal distribution. So I'm going to go through the equations here so that you can understand where these numbers are coming from. So a squared is this funky relationship here. So n is your number of samples. That's pretty standard across notation. Your a squared is the Anderson-Darling test statistic, and yi is sample I of your ordered data. And I'm going to have a more in-depth video on the Anderson-Darling test statistic and the Anderson-Darling normality test, as well as the Ryan-Joyner. Right now I'm working on an Excel worksheet that you can plug data in and it will analyze it for you. Once I finish that, I'll go through how to use that and I'll post it so that anyone can use this. But for now, again, this is just high level. We'll get into it more later, just kind of some background. And then your f of y is the cumulative distribution function. Okay, so what this means is you take your data and you order it from smallest to largest, and then what you do is you plug that into the cumulative distribution function. So that t there, what you would end up doing is you would integrate that from negative infinity to x, and x is going to be your your yi, right? So f of sorry, I should have had these in a different order, but this f of x is the same as f of yi. You just plug in yi up there, and so you would do that for each individual point, and then you would sum them all up as it's shown here. So you do that for do that for each of them, sum it up, and then that gives you the Anderson-Darling test statistic. So we then use that to calculate the A prime, and how you do that is you multiply the AD test statistic by 1 plus 0.75 over the number of samples plus 2.25 divided by the number of samples squared. And then you use these correlations. So these correlations, you don't have to memorize any of this stuff. This is just helping you understand where these numbers come from. So depending on where it falls into these buckets here, less than 13, greater than 0.6, or all of these different buckets, you plug in your A prime, and then you would solve to get your p-value. So when I go in more in depth, I'll explain what I'll kind of show you what each of these correlations do for you, so that you can kind of understand it and make your initial guess of the p-value based on just looking at the AD statistic rather than actually have to calculate it, because part of this is being able to understand where your numbers come from and what they mean rather than just plug and chug, because statistics isn't an engineering problem. It's not plug and chug. Okay, we got a p-value of 0.06, it's good to go. Well, 0.06 isn't that great, and depending on your significance level, that could be passing or failing. You have to really understand what's going on in your data, which is what makes it tough, because data science can be kind of subjective. Not really, but there's some things that seem very arbitrary until you understand where they're coming from. So interpreting the results, like I said, generally the significance level is 0.05. So if your p is greater than that, the data approximately follow a normal distribution, and that means that capability indices and other statistical analyses are assumed to be valid. So if it passes the Anderson-Darling, we say, okay, yep, we're going to assume it's normal, and now all of our tests that we run on it that assume normality, they're all considered to be valid. So moving on, what happens if your Anderson-Darling fails, or maybe you just want to do a different test? There's also the Ryan-Joyner normality test, and it's often used because it's not heavily influenced by the tails of the data. So what the Ryan joiner does is it actually calculates a correlation between each data point and its normal score. So it's a correlation, it calculates a correlation coefficient. And if the correlation coefficient is less than the critical value, then the data fail the Ryan joiner normality test, and we reject the null hypothesis. So the reason this is used is because it focuses it focuses in on something different. So data can fail the Anderson-Darling, pass the Ryan-Joyner. Data can fail the Ryan-Joyner and pass the Anderson-Darling. Because they're both measuring in different spots. Anderson-Darling measures on the tails, whereas the Ryan-Joyner measures each individual point, and it's much less. It's not. Um, the Ryan-Joyner is not dependent upon the entire set of data the same way the Anderson-Darling is. It's a lot more complex than that, but that's kind of how you can think about it. So how do you calculate the Ryan-Joyner test statistic? That is the sum of yi minus y bar over b. And I'm not going to read that out. You can read it if you want, but I'll really explain what these are. So again, RP is the RJ test statistic. Yi again is your ordered data. Y bar is the mean. And then BI is the normal scores of your ordered data. S squared is the sample standard deviation, and N is the number of samples. Everything here is pretty straightforward except for B, the normal scores of your ordered data. So I was having a lot of trouble when I was trying to make my Excel macro, because when I heard normal score, I thought z-score, because that's a normal score. Well, there's actually another type of normal score. Okay, I didn't have it on here. When I go into more depth on the Ryan-Joyner test, I'll explain that. But what the normal score is it's not the normal score of the data point with respect to the distribution. It's the normal score of its location. Now that doesn't really make sense, but let's say you have 100 samples, and instead of taking the normal score of yi, you're actually taking the normal score of I. So if you have 100 samples, bi of 50 wouldn't be, let's say sample 50 is 3, so 3 inches long is sample 50. You wouldn't take the normal score of your 3, you would take the normal score of the 50. And like I said, I'll go more in depth, but that's really where the hangup is. If you go on Wikipedia, they have both definitions. Go with the one that isn't the z-score if you're curious, but like I said, I'll go over this later. So the critical value, I was having trouble finding a correlation to turn it into a p-value. Maybe when I go more in depth, I can actually use the p-value, but I've just been using the critical value for now, and it's been giving me good results. So that's calculated using this equation. Again, n is the number of samples. So interpreting the results, the null hypothesis is that the data do follow a normal distribution. The alternative is that the data do not follow a normal distribution. So if your test statistic, RP, is greater than or equal to your critical value, then we fail to reject the null hypothesis. So that means that the data approximately follow a normal distribution. And again, since we assume it's normal, all of our statistical analyses that depend on that assumption are considered valid. So finally, the skewness kurtosis. Skewness and kurtosis are measures of the shape of a normal distribution. For a normal distribution, skewness is 0 and kurtosis is 3. So these are kind of like the properties of a normal distribution. So the shape, this is how you measure what the shape is. So kurtosis is a measure of how heavy the tails of a distribution are. Positive kurtosis means that the distribution has very light tails. Negative means that the distribution has heavy tails. I don't have my pictures. When I go more in depth into the skewness and kurtosis, I'll give examples. But if you just look it up, you can see. So like positive kurtosis means that at the tails it looks very kind of like an exponential distribution where it increases slowly as you get toward the mean, and then it starts increasing more and more rapidly as you get to the mean. A negative would be where it actually almost the increase seems to slow down. So if you were to take the derivative of it, As you get closer to the mean with a positive kurtosis, the derivative would increase, and with a negative, it would decrease. So skewness is the lack of symmetry in a distribution. It basically measures whether or not the data fall to one tail or the other. Positive skewness means that the tail is on the right side of the mean, and a negative skewness means that the tail is on the left side. So that means that on the everything's going to be bunched closely to the mean on one side, and then it's going to be long and drawn out on the other side. So how do we evaluate this? Well, skewness and kurtosis are actually they're actually moments of the mean. I'm not super well versed in what moments are. I'm not a physicist and I'm not a statistician. I am an engineer, so I care about the high level of this stuff. I would like to get a little more in depth in my further videos. Maybe I'll explain that more when I get to this one, which probably won't be anytime soon. There are other more important things within quality engineering that I would like to touch on first. So skewness and kurtosis, here are their equations. Xi is your ordered data again, X bar would be your mean, and N is the number of samples, sigma is your standard deviation. So we use the skewness kurtosis if normality has failed and no normal distribution is found to be a good fit. There's a few other tests in there. There's transformations. So this is your serious last resort because it's not very sensitive to the data at all. It just says, okay, does it kind of look like the shape of a normal distribution? And how we do this is we use the Jarque-Bera goodness of fit test to determine whether or not the data follow the distribution. A JB value of close to 0 means that the data closely follow a normal distribution. So the S there is your skewness, K is your kurtosis. So the reason that K is -3 is because we're actually using an adjusted kurtosis. So like I said earlier, in a normal distribution, kurtosis is 3. So we subtract the 3 to show us, okay, well, how far off is our kurtosis from a normal distribution? And that's how we get that the JB value when it's close to 0 means a good fit. So the Jarque-Bera test follows the chi-squared distribution with 2 degrees of freedom, but it's a lot less sensitive than the chi-square goodness of fit, which makes it great for a last resort, especially when small sample sizes are used, because small sample sizes you're generally not going to have a normal distribution, because like we talked about with the central limit theorem, not only does that mean that as you take more samples you should get a more normal distribution, but it also kind of means the opposite. With less samples you'll get less of a normal distribution, which makes sense. But we use this because, like I said, it's just like, throwing paint at the broadside of the barn. You're probably going to hit, because you're just saying, okay, take your glasses off. It's kind of like the fat pencil test, which I'll be going over. It's okay. Does it kind of take your glasses off? It's blurry. Overlay a normal distribution with the mean and standard deviation. Does it look like normal distribution? Yeah, kind of. Okay, good. But we can add, this is actually a way of measuring it, unlike the fat pencil test. That's basically an attribute. This we actually get real data from. So this is a variable. So how do we interpret the results? Well, we use a chi-square distribution to convert the JB test statistic into a p-value. You should use statistical computing software to give an accurate or precise result. Otherwise, you can use a chi-square table with 2 degrees of freedom to determine whether or not you're passing or failing. It won't tell you how well you're passing or failing, just whether or not you are. So the significance level alpha, again, determines what p-value is considered critical for rejecting or accepting. Generally, it is 0.05. That's pretty much the standard. Different industries might do different things, but that's kind of what's considered standard. And for the Jarque-Bera normality test, the null hypothesis is actually a joint hypothesis. What it says is that the skewness is equal to 0 and kurtosis is 3, which therefore the data follow a normal distribution. And we're basically saying, giving a p-value of whether or not that's true, which basically just says, okay, that's if we have a p-value of 0.10, which would be passing. All right, there's a 10% chance that this distribution follows it, which is good enough for us because we don't have enough samples. If we were to extrapolate it out, eventually it would get up to 100, right? Um, so this all this alpha stuff, what does that mean? In statistics, there are these things called type 1 and type 2 errors. The normality tests discussed so far are what are called hypothesis tests. And in statistical hypothesis testing, there are two possible types of error. A type 1 error, which is a false positive, which means rejecting the null hypothesis when it is true. A type 2 error is a false negative, failing to reject the null hypothesis when it is false. So here's a graph of it. This chart is often used to explain type 1 and type 2 errors, and it's great. It is great for that. So on the in your rows, that is your decision about the null hypothesis. So you can either choose to reject or not reject. Well, not reject or reject in this case. And then the columns represent what the actual value of the null hypothesis is. So if the null hypothesis is true and we choose to not reject it, so we say, yep, it's true, that's correct. That is the correct answer. The null hypothesis is true. We failed to reject it. The probability of that is 1 minus alpha. That's the definition of your significance level, right? It's the probability of rejecting your null hypothesis, which if you go down for the type 1 error, like I said, is the false positive. So that is, and in this case, a positive test is rejecting the null hypothesis. I just want to make that clear. I don't think I did. So if you have a positive test result, you rejected the null hypothesis, okay? If you have a negative test result, you failed to reject the null hypothesis. So a type 1 error, the probability of that is alpha, because like we said, the significance level alpha is the probability of rejecting the null hypothesis. Okay. There is a type 2 error, which is the false negative, failing to reject the null hypothesis when it is false. So that means the null hypothesis is false, and we said, based on our data, we think it's true. The probability of that is beta. We don't use that one too much. I'm not sure why. Like I said, I'm fairly new. I don't really care about the statistics behind it. Maybe I'll get more into that when I talk about statistical hypothesis testing. But for now, it's beta, and the probability of getting the correct answer of rejecting the null hypothesis when it is true is 1 minus beta. So now we've pretty much touched on everything. Now we just got to wrap it up here. So the reason we have multiple different methods is because a data set can fail one normality test but pass another. Now, does this mean that the data isn't normally distributed, or that it is? Well, data can fail one normality test but pass another because different tests examine different areas of the distribution. And this can lead to a test rejecting the null hypothesis when it should be accepted. That's your type 1 error. So like if it fails the Anderson-Darling but then passes the Ryan-Joyner, that would be a type 1 error in the Anderson-Darling. Okay, so when we're assessing our data for normality, we can't rely solely on the results of the test. Like I said, this isn't plug and chug. You got to look at the data, understand it, and it helps to know where these numbers come from. And this is especially important when you're analyzing departures from normality, because the distribution and the shape of the data can actually reveal a lot about the process. Different distribution shapes generally correlate with different failure modes. So I'll go more into that when I do my non-normal distribution identification video. But for now, what the key concepts are: normality is important because of the central limit theorem and because of capability indices. I'll touch on both of those a little bit later, especially the capability indices. That's very, very important. But we like normality because it allows us to take less samples, and it allows us to make judgments and assess things about our data using a small sample size. So that's it. This probably got a little long. I hope that if you stuck through, you really learned a lot. You enjoyed some things. Thank you so much for watching, And as always, have a great day and do something awesome. Thank you.